Hello, this is David Choi, and I am presenting about convolutional recurrent neural networks, learning spatial dependencies for image representation, which is published by these gentlemen here. So this presentation includes sections taken from the project poster, specifically the introduction, which is what we will be talking about in summary. The materials, what does the paper provide in terms of visuals and results? Methodology, theoretically, how are we to apply this before we jump into the code? Results and demos, the paper testing results reported and code snippets extracted from a GitHub, which goes over convolutional recurrent neural networks. And the conclusion, what is to be done next, my opinion. So it is made up of the convolutional neural network and the recurrent neural network mixed together. So the convolutional neural network is made for extracting spatial features, but may struggle with sequential tasks, such as handwritten text, video, and etc. Convolutional neural networks have had a significant impact on the advancement of computer vision, especially in image classification, detection, and facial recognition. They're designed with a convolutional and pooling layer, among other layers, like the fully connected layer and the activation functions in it, which allow it to detect spatial features quite soundly. However, its independent processing of local image regions limit its ability to capture contextual dependencies, which is where the recurrent neural network comes in. The recurrent neural network, or RNN, is designed to handle temporal dependencies, relationships between elements in a sequence, not the local elements themselves, but not to effectively extract spatial features like the CNN does, such as edges or shapes. To solve this issue, we combine and integrate them. Like I was saying, RNN is designed to learn dependencies across time and understand how previous states influence the current state, allowing them to retain and process information over long sequences of inputs. So basically, they can retain information from previous inputs, which the CNN cannot, and understands correlations between different parts of the sequence. However, in the image domain, there are no predefined sequences, since images are usually treated as static. Convolutional recurrent neural networks, which are a mixture of the two, combine the feature extraction capabilities of convolutional neural networks with the sequential modeling capabilities of recurrent neural networks. The CRNN framework is a proposed combination of CNN's spatial feature proposed by this paper, recognition capabilities with RNN's ability to capture process sequences and learn spatial dependencies between regions of images. With this framework, we can combine the spatial features extracted by CNN with the spatial dependencies learned by RNN to enhance image comprehension. So CRNN's melding of CNN and RNN provides a solution for the former's inability to garner contextual dependencies by using RNN's innate learning design. And the latter's issue is also fixed by converting the 2D spatial structure of an image into sequences that can be processed. And I'll go over how that's achieved a little bit later. The CRNN achieves this by scanning an input image in multiple directions, left to right, right to left, top to bottom, and bottom to top. By scanning the image in several directions, the function transforms the image into 4 sequences of region. For the next slide, I'm going to go over the next 3 slides first because there's some important information in the methodology section that goes over what these mean. So the key components of the CNN are the convolutional layers, the pooling layers, and the fully connected layers. The convolutional layers, like we talked about in class, applies a set of convolutional operations to images for the purposes of detecting local features like edges, lines, etc. For example, the Sobel filter, so 3x3 matrix, is slid over images, detecting edges by emphasizing the differences in neighboring pixel values. Ultimately, this ends in a feature map. The pooling layer reduces width, height dimensions of the feature map, reducing size and consequently increasing computation efficiency and robustness. There are several types of pooling, but max and average pooling are the most common. For example, a 4x4 matrix can be effectively reduced to a 2x2 by taking the max value of each of the four 2x2 subgrids. So the 4 up here, the 4 up here, 4 up here, 4 down here, and the 4 down here. Just taking the max of those and making it into a 2x2. So the fully connected layer have neurons with full connectivity with neighboring neurons, which helps to integrate non-local learned features when generating the final output. For example, it can take a flattened vector of a feature extracted map and use it to create a final output, the class probabilities. RNNs are designed for processing sequences of data, allowing them to capture temporal dependencies by maintaining a hidden state, which is basically just a set of vectors that stores info about previous elements in its sequence. So this hidden state is updated at each time step based on the current input as well as the previous. And that's basically how it learns and captures temporal information. So that's what this is showing right over here, looping through the hidden state with its current as well as previous, exemplified by this formula here. Within this figure 1 formula, WHH and IH are just weight matrices. BH is the bias, and F of H, which contains all of this, is the activation function. The output is generated at each time step using the current hidden state as well as the previous hidden state, H of S minus 1. And that's all stored in the current H of S right here. And in figure 2 formula, WHO is just another weight matrix, B of O is the bias, and F of O, which contains all this, is the output activation function. This all stores in the current Y of S. And the activation function is just a way of introducing nonlinearity to the network. Of the CRNN. The CNN component consists of 5 convolutional and pooling layers, which detect and extract the middle level features from the input image. The RNN component captures spatial dependencies between regions of the image by converting the output of the CNN layers into sequences. And then the CNN feature maps are scanned in 4 directions, as previously mentioned, creating 4 sequences of image regions. That was showed in the visual. Each sequence is then processed, and the dependencies between directional regions are learned by the RNN. And this is just going over figures 3 through 6 and figure 7, which combines the different hidden states, 3 through 6 and number 7. Then the combined features from the RNN layers are fed into 2 fully connected layers to learn a global image representation. So for the code portion, I'm going to be going over the pertinent CRNN code from this GitHub. Unfortunately, I could not get the demo working because the dependencies that it relies on, at least one of them, were not compatible with my system. Nonetheless, I'm going to be going through the important snippets of code, laying out what it's doing. So this is the helper function for adding convolutional layers, followed by the ReLU activation function. These are just the input and output channels for the current layer. Then we add a 2D convolutional layer. Optionally, we can add a batch normalization layer here, and this is the ReLU activation layer, or the ReLU activation function that I was talking about earlier. And this, the next part, which utilizes the helper function, which I blew up over here, is also adding the pooling layers. So as you can see, we're stacking the different layers. We're just running this through several convolution layers and several pooling layers as well. 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4. Okay, and self.cnn as part of the fully connected layer, we're assigning the CNN to a class variable. And for this, we're defining the bidirectional LSTM layers. And LSTM basically just stands for long short-term memory, which is a type of recurrent neural network architecture that's designed to better capture long-term dependencies in sequential data. Just defining the bidirectional LSTM module. Bidirectional meaning it goes left to right and right to left. This is the bidirectional LSTM layer, the linear layer to map LSTM output to the desired output size. Oops. And this is passing input through the LSTM layer. This is getting the size of the LSTM output. We're reshaping the LSTM output to a 2D tensor, passing the reshaped output through the linear layer and reshaping output back to the original dimension. So in conclusion, I found this project to be pretty interesting in that we can combine two separate neural networks and make them work to compensate for each other's lacks. I think that's pretty cool. And in doing so, we create something which outperforms other established frameworks of image classification. There are a variety of use cases in image classification, scene understanding, object detection, handwriting recognition, medical imaging, and even autonomous driving. These are the use cases that I found. Anything which requires both spatial and temporal understanding. Further experimentation is necessary for different applications since the author puts forward CRNN for a particular set of image analyses tasks. Thank you very much.